Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So thank you for attending. So I'll talk about, the talk will actually have two parts. The first part about convolutional neural network for automatic speech recognition, and the second part is about deep model for ASR without using HMM, which is a segmental model, a new proposed segmental model. So let's start with the first part. First, the convolutional neural network was invented for image recognition by Ian LeCun in the mid-90s. And it provides invariance for translation, and as a result it gets more robust against scaling, rotation, and noise, and it provides state-of-the-art accuracy on image processing or image recognition tasks. So for speech, we also need to have some invariance for small frequency shifts. For example, the same format can come at a range of frequencies, maybe a higher or lower frequency. So we need some invariance for that. Also, along the time axis, the speed rate may be different. For example, for our neural network, we have like 15 or whatever number of frames as an input. So maybe some invariance along the time axis may help. So we will see how this is done for speech recognition, and we will talk about the results. So the basic idea is that first, each node of the neural network takes a local input, and nodes receiving input from different parts of the frequency have shared weights, and then we pool nodes from with different shifts together to get some high-level features. As we see in this figure, we have the speech, this segment of speech along the time axis and the frequency axis, and this figure represents the filter bank feature. Then we have the convolution layer. In the convolution layer, we have a number of these plates. Actually, in our experiments, we have 84 of these, and each one of these plates represents a feature map. Each one of these plates represents a feature map that has its different weight metrics. And this weight matrix only looks at a local part of the spectrum, not the whole frequency axis. And this weight is shared between all these nodes. So, for example, this node will receive, will have the same weights, but will receive input from lower frequency. I'll shift the frequency by one filter bank. And this node will receive input from this part. So here I'll have like the same filter convoluted with this part of the speech segment, and then in the next layer I have the max pooling layer, and I have the same number of feature maps as the convolution layer, and each node of the pooling layer just takes the maximum of, for example, in this figure, from these three nodes.
So each of those columns is looking for a specific parameter.
Yes, yes, right. Yeah.
And what's going on with the static delta and double delta?
So actually, each node receives the same part of frequency for static and delta delta. For example, if this receives from like 15 to 25, it receives, for these bands, it receives also delta and delta. Then comes other fully connected layers, 1, 2, 3, whatever the number. And for this model, we can get on Temet 21.6 phone error rate accuracy. And for that model, we used filter size 8 bands of the filter bank, and pooling size 6. So this size is 6. And we shift, each pooling node receives shifted input by 3 nodes, like this.
How is this? So this is different from what you did with Abdelhamid.
Yeah, this is the standard version of convolutional neural network, but on 1D. This is full weight sharing. In the next slide, I'll show the improved version, which is in the paper.
So this is not what you did.
This is overview of the standard convolution. I did, and just for comparison between full weight sharing and limited weight sharing here. So the idea that instead of sharing the weight along all these nodes, because in speech each frequency band may have different features, so we divided this to a number of segments, and each segment has its different weight method. Yes, yes. Yes. For both. Yeah, recognition for Temet, phone recognition. Yeah. For example, if our window is 15 frame or 11 frame. 15. For this experiment, 15.
So this is what?
Yes. Yes. It's the same as the DNN.
This is what was in the previous.
Yes, right. And I implemented this. Also, there is one extra modification, that each of these nodes takes, in addition to this, these bands, takes the energy band as an input. Because I tried first without the energy band, I got this score. But with the energy band, I get some improvement. Yes. No, for the whole window. Sorry, for the frame, yeah, for each frame. Yes, but this node doesn't see the whole spectrum, so it can't compute the energy of the whole spectrum. So actually, this model the same as the one that was in the paper, the ICAS paper. And then I have tried some ways to improve the model. So I have first tried to use multi-pooling sizes, then learning softmax pooling weights, pre-training, and add time domain convolution. So for max pooling, it adds invariance to small frequency shifts. But if the problem is that for some phonemes, maybe I lost some classification power, discrimination power. So in this experiment, I try to use different pooling sizes for different feature maps, as we see in this figure. So some of the feature maps has pooling size of 3, and some other feature maps has pooling size of 2. In my experiments, I tried having many groups. Each group has different pooling size, and for the best configuration, I get some improvement, and I get this score, 19.72 phone error rate on Temet, and actually this is a new record.
So that number actually, I was reading the number, I spent a while running 120 rather than 84.
Okay, yeah. Yeah, this is just for explanation. So the parameters of the model were 180, right? 120 feature maps, and pooling size ranges from 1 to 12 or 10. So
This is going comparing how many nodes
feature maps, I mean by feature maps how many columns here. Because each column in this new model, in each column I have a set of different weights also. And it's determined by how many elements in the frequency and how much I shift each node here. So for example, if the shift is 2, I'll have 20 of them. If the filter bank size is 40. And this shows some results on Timid, and without using adaptation, we get the best result using this model. 2 fully connected layers, 3, and this model 3. Yeah, 3. Yeah, and each layer 2,000 nodes of the fully connected one. Yeah, yeah, and they use speaker adaptive training also. So the other modification, the motivation for this, we thought instead of like specifying how many how many feature maps per each pooling size, we tried to make the neural network to learn the pooling weights automatically by using this soft max function and adding weight on each arc to the pooling node. So in this figure, I just get the maximum, but for the softmax, each of these arcs will have some weight, and then the pooling output will be multiplied by this softmax weight, which is from 0 to 1. So, so for example, if I set the pooling size, for example, to 6, and I have 6 weights, after learning, maybe some of these weights will be near to 0. So actually, the neural network will learn to get to set the pooling size, for example, to be 5 or 4 or 3, if it needs to do so. So here these are the weights, and these are the outputs of the convolution layer. So if I have 6 pooling size 6, so I have 6 nodes, 6 of these O's, and each one will be multiplied by this weight, exponential of W, and then normalized over the total sum, and then multiplied by the node output. So actually this will make more impact to the nodes with high weight value and less impact for the nodes with low weight value. On the weights multiplied by the values. Yeah. Yeah. Yeah, W plus O. The reason why I used exponential of W, because I want to restrict W from 0 to be greater than 0. Greater than or equal to 0. Just the sum from node 1 to node 6 if the pooling size is 6. J is the same. And B and K are the band, the output band, the pooling band, and K is the feature map. I tried to learn this model. I got a very small improvement here, but if I increase the pooling size, I get worse results
Is this on the test data or the test data?
on the test data.
And you optimize on the test data?
Optimized on the training data, the weights. The weights are optimized during training on the training data.
But making the decisions about the different, parameters, what was best to transfer, like how many blocks, all this kind of stuff, that would make those decisions like this. That's
Uh,
There is a test data, but that data
Yeah,
is
yeah.
mainly used to tune, what was it, tune the training effort. Your that will change that test. So, if you use that test to tune everything else, everything is just one number. You don't know what's the effect of the effect. So far, that's that.
We don't
well, which parameters for?
Right, it could be a random fluctuation on the test bed.
If the difference is small, it may be. Yeah. So what I said is that just very small improvement on one experiment and worse result on another. So it doesn't have like much gain to learn these weights compared to setting them by hand. And these are the weights that are learned on one experiment. I had 3 groups, and the black means the weight is near to 0, and 1 means the weight is high.
It's slightly better than without doing the whole month.
Yeah,
With a fixed one.
yeah, yeah.
20 point.
But it may be just fluctuation because it's a very small difference.
Other experiments not doing
I didn't try with average pooling, but I guess so, but I didn't try.
I think that's what it is.
Yeah. Sure. Then I tried to do pre-training for the convolutional neural network. And the motivation is that RBM pre-training helps with deep neural networks. So I try to use this convolutional RBM proposed by Hoglan and Lee and
So in that case,
others.
applies to EM as well, the upper layer?
The upper layer are trained using standard RBM, but the convolution layer is trained using this convolutional RBM. So in the convolutional RBM, for example, if I have 6 nodes pooled together, the probability, instead of being binomial, if you are familiar with the RBM, it will be multinomial. So it will be either one of the 6 nodes or no one. So it's one from 7.
So the code that has been running, I didn't see that RBM training for EM, because you already trained the system into EM.
No, because I trained for example, the first layer is convolutional layer. I train it, then I train the other layers using the RBM training. So I train the first layer, I fix it, then I compute the output, then train the second layer, and so on.
All the RBM.
Yeah. Mhm.
You might have said this, but is the stock max pooling, or the max pooling, is that max pooling or is it stock max pooling?
Max pooling.
How do you take derivatives from max?
That the derivative is only passed to the maximum. So I keep track of which node is the maximum during the forward iteration. Then during the back propagation, I only update the maximum one.
That's pretty standard. Not obvious. It's not
Yeah, the idea for this pre-training is that these 6 nodes will share the weights, and the maximum of these will get the maximum like update, and the least one of them will get 0 or very small update. Yeah, there is a mismatch between the definition of this RBM max pooling, this soft max pooling, and the max pooling I use and afterwards in the fine tuning. And then I did this experiment on Timid, but I used one hidden layer. I got worse results, so still I am running some experiments. But on HVT, I tried pre-training, and I got some nice results. So first, deep neural network without pre-training. This is the standard neural network. I get 37.1 phone error rate. HVT is the voice search data set we have here in Microsoft, and I used a subset of 18 hours just to get the results quickly. And on this data set, actually pre-training helps a lot. I did this experiment using my MATLAB setup. Yeah, random. No, random initialization. So pre-training helps from 37 to 35.4 with DNN. With CNN, without pre-training, I get 34.2, and then with pre-training, I get 33.4. And then using the multi-pooling sizes, I get a little bit better, 33.2. But also with Eric's setup, he got actually better than my setup with pre-training. And I think that the main difference is the pre-training. I mean, without pre-training, I get similar results. I mean, when I use his pre-trained model, but yeah, I think I mean the DNN tool pre-training is a little bit different. It does some tricks to optimize.
Before you finishing tomorrow, we need to get that final.
Yeah. Hopefully we can get even some better score for convolutional neural network. Yeah. The problem is that it's very slow on HVT. In OT now.
So that's why. So do you think it's like, I think in our earlier experiment, 24 hours of voice data, we can still,
Very slightly.
Yeah, I think the problem over here, if you can try to see the way you did it, pre-training, it is initialization without pre-training in terms of the scaling and in terms of feedback stuff.
Yeah, I ran smaller number of evokes, and mini batch size is a little bit different, and the learning rate. Yeah.
So initially you need to noise
Yeah, I didn't do that. So yeah.
I think 24 hours and 18 hours probably similar size. And also, what is the scaling of the random initialization for DNA without pre-training?
I think I used the same scaling, 0.01. 0.
Yeah,
Yeah, 0.1.
Because with your internet, actually said that if you make that with even smaller as a function of deep learning of each layer, what level is more about the distribution? And do you have a similar? I don't know how small it is.
No, we try to show different incarnation using similar results. But if you already
Similarly good or similar bad? How good it is? If it is deep, so a little bit more.
But if you already have some network and you shrink all the way by 10, then you use that as your pre-training model.
Yeah, that's good.
You know,
Yeah, that's what I thought. That's good. What I thought.
Yeah, yeah.
So it's about 10% lower than the other, or whatever, maybe my time.
probably was only 10.
Yeah, yeah. To go to the next more interesting part. And the last modification was to see if the time convolution helps or not. So previously I used frequency domain convolution, but here I use time domain convolution. So each node receives part along the time axis. And then I do the same stuff. And actually some people have done that before, but for example, Hoglang Lee has done that on to learn unsupervised features of speech, and he got some nice results by using SVM for frame
Your
classification.
frame size, if it was 15 frames, for example, that would you should how many?
No, for example, if my window is 15 frames, each node of these receives smaller size, like 8.
Within 15.
Yes, within 15. Then I keep shifting and then pulling.
I'm sorry. How is this different from the previous one, except that the blue box covers now all the frequencies?
The shift will be along the time axis.
The other blue box covered all the time.
Yeah.
Much bigger frequency.
So the previous one,
Right. So there, the blue box.
here the blue box shifts along the frequency axis
Right.
and takes the whole window of the 15 frames or the 11 frames.
Okay.
But here,
I think completion is that
On this other picture,
it's possible to be.
yeah, I think this is about beginning.
Yeah,
maybe it's
yeah.
So it's just taking.
taking a smaller part.
Okay.
How much you have? That's about, that's 15, right? If this one to be about 5,
Yeah, maybe the figure is misleading.
So
but
it's taking a smaller box and shifting a little bit
Yeah.
along the time axis.
yeah, then I do, yes,
Are you doing the same trick with
No.
go through and skip the way you skip? I mean, if
Uh,
you go through and then have them then new weights and Sarah through and new weights.
no, I tie the weights along the whole time axis. Because because here the same features will happen along any part of the time axis.
Because you could learn the center tone and left tone by convention.
Yeah,
To learn it
yeah,
center tone to do a separate thing.
yeah.
So the Eric loop, one to two,
Eric did some combination.
combination on the
Also with CIT.
Mhm, mhm. Yeah, yeah. So I tried to compare using time convolution alone against the standard deep neural network. For some parameters it helps, and for some others it didn't. But I think maybe because I used, for example, this here I got worse result. But I think because I used a smaller number of feature maps against the 1024 nodes of the fully connected deep neural network. But here I shift, so I have so many outputs in the convolution layer. Yes. Yeah, 400 of these. Actually, this is much more than the size done in image. In image, usually you have small number like 20 or 30. But here in speech, I need to use much more.
400 sets of waves.
Yes.
Each one involved across the whole.
Yes. Along the whole time window, temporal axis.
So parameters the weight here more than the system.
No, because I have full weight sharing. So
Oh, it's here. I see. Yeah, this one has Eric only did like 10.
yeah. Yeah, for example, when I used 400, I got, with the same set of parameters, I got better score even than the DNN. But here I tried to use bigger shift, and I lost some score. This may mean that if I use more, even more feature maps, I may get better score.
So you give them 15, and then you give them how many for each band?
So
15 frames, right?
each filter has eight
Eight
frames.
frames. Okay.
Yeah, number of frames,
8.
and pooling size is 2.
You get a higher one.
Yeah, in the pooling layer.
So what do you use more?
I try to like increase each parameter one by one and see the progress.
You don't have
Yeah.
Okay, so
Then the next idea is the normal thing, to combine both frequency and time convolution. I did this part, but still the parameters needs optimization. But maybe later. The problem of my implementation that I did, the full weight sharing. So it may not get as close as the limited weight sharing, but at least we see here some improvement of convolution along time. Maybe if we combine full weight sharing and time convolution, I'm not sure, we may get some improvement on it.
all these probably without that set. You think that you're not going to do that without that set. So many
Oh yeah.
that's a little manipulating having properly.
Yeah, because in this part I have many parameters. The filter size along frequency, filter size along time, pooling size along frequency, pooling time along size along time, shift, frequency and time. So many parameters to optimize. Yeah.
But in terms of level of parameters, what is the which aspect of the height level parameters?
So the fully connected will have the highest number of parameters, but it depends about on the parameters that I use. No, actually, for the best performing convolutional neural network, I tried to match the same number of parameters of the fully connected by increasing the number of feature maps. So, in conclusion, CNN improves, convolutional neural network improves the results over the standard deep neural network. And it provides a method to incorporate our domain knowledge in the structure of the deep neural network. And number of modifications have been presented, multi-pooling size, and it brought some improvement with its softmax pooling, but not much improvement using this. Pre-training, it brought a significant improvement on HVT dataset. Time domain convolution also is promising if we combine it with the frequency domain. So maybe we'll do more experiments in the future to try this. So now we come to the second part, the segmental model. So just overview of segmental models. In segmental models, scores are computed for the whole segment instead of the frame-based, where I have score for each frame, then I sum or multiply for the whole utterance. And some work has been done in the some previous work from the 90s for the segment model, but I think it couldn't beat the HMM model. So the motivation for this segmental model, that the hybrid deep neural network HMM model, first, many independence assumptions are violated. For example, it assumes that each frame is independent from the previous and next. Although I use the same set of frames, only I change one frame from the 15. And the posteriors of the neural network has to be converted to likelihoods, then fed into a generative model. The targets, neural network training targets, are different from the desired objective, which is the label's posterior probability over the whole sequence or the word error rate. So here I consider the objective is to optimize the probability, the posterior probability of labels given the speech utterance. So I try to compute this posterior probability directly by assuming that I have some segment scores and some language model scores, and then I take the exponential of this and normalize over all possible sequences. So I get.
How is this different from the segmental CRF stuff that we did in 2009 and 2010 and had a workshop on?
I think you may answer this question better.
S is coming from pre-neural network, not from anything else.
I think you try to use the neural network to optimize to use neural network posteriors.
What you have there is the same.
But what I have here, I don't have here.
It's S is different. I think it's S is different. I think should be that's the purpose of segmental model.
The segment part is the same as before.
Assuming glass in the model.
That's not just glass.
No, the concept is that the score is defined in the whole segment. That concept. Yeah. No, I think
But he used a generative model for not.
Yeah, he had some weird anti-phone models for different phones.
Mhm.
That's so segmental CRF of what is S then?
S is a set of segments. Consider all possible segments.
Mhm.
Not S. S is the score.
Right, so you compute a bunch of scores based on that segment. And then those scores get weights.
And from where do you get these scores?
The scores come from detectors. For example, you might have a phone detector, a multi-phone detector, a signal
Mhm.
detector, or there's a lot of different.
Yeah, and how do you compute these scores? Is it posterior probability of this feature, or
So the simplest way
is
of
it
thinking-
0 and 1s?
The simplest way of thinking is just zeros and ones.
Mm-hmm.
But we've also put in scores like, well, the HMM probability for this segment
Mm-hmm.
being labeled by this particular label
Yeah.
is such and such.
Mhm.
So you stick that score in.
Mm-hmm.
I think at that level.
Um,
And then
So-
these all get
Yeah.
weighted
Mm-hmm.
and then exponentiated.
Yeah. So the main idea.
Of normalizing over
Yeah.
all possible
Yeah.
segments. So the CRF does,
Mhm.
so this is the segmental CRF that you have to-
Yeah, so it is similar, but the difference is that the score, I assume that the neural network will learn how to score, to compute this score for this segment. It is.
I think that's the only difference is that
Mhm.
basically you're back propagating
And
through the network.
another difference is that, for example, CRF, you include the previous label, for example, but here you can include the previous and next label. You don't have any constraints about how you define the language model score, for example.
No, you do when you actually go to decoding. So in this
segmental
Yeah, for
CRF,
decoding, if you get a complex language model.
Thing that we did, we actually went to significant trouble
Mhm.
to incorporate a full finite state language model, which I'm sure is discussed.
Yeah, and in this experiment, I use bigram for decoding, but for rescoring, when I have the full label sequence, I can rescore the whole utterance. So I can, in that case, I mean, within this model, I can use whatever complex language model, whatever powerful neural network to compute the score of the segment. I mean, the idea of exponentiation and normalization, it is, well known in the machine learning for the undirected graphical models. But I mean, the idea is here that I assume I have a number of segments and I'll make the neural network to learn how to compute this score.
So how does the method model get incorporated into segmental CRF? In the same way, or
So there's a transition function between labels. So you have the segments labeled by something, and what you label them by is actually states in a finite state language model. And what that means is that when you go from one segment label to another, you're essentially taking a transition in a finite state language model. And that finite state language model can be a 5-gram, a trigram, a 4-gram, any kind of finite state language model you need.
Mhm.
at the word level, at the segment level, combination of those.
At whatever level you're defining the label.
But here,
Mhm.
he bypassed all this problem because in Timid, he only.
Yeah, in Timid I used bigram.
It's
Bigrams, it's easy.
All the problem is
If I use more complex language model, I have to do beam search and for training it will be complex. I need a lattice to
maybe the trick.
optimize the whole sequence.
You have to check how they work. But you were able to do them tomorrow, no?
Yeah.
Second time, not the third. We couldn't do it. If we could try grand model, we could even do that.
Well, you have to prune it.
Oh,
So
I
in the
see.
right.
Okay.
Yeah. In the workshop we did lattice rescoring at the word level. And since then I played around with phone decoding at the phone level where you can deal with some of these things a little better. But you do have.
So exactly, and then I was like, you just learning more into learning stuff.
Yeah, the motivation for this model is that we have neural network compute some nice scores.
Right. I would call this a segmental CRF if you know that feature.
With the joint.
Yeah, so, but here you will consider the features, the lower layer, not the top layer, right? So that you are weighting the, not the last label layer, but the layer before the last one.
This is a CRF. And since it's operating at the segment level, it's a segmental CRF.
So when we talk about this, so we talk about this is the segmental model
Mhm.
that incorporates the neural network output that to determine what kind of segment is flow.
Yeah.
Okay.
The fact that you're normalizing over all possible segmentation
I see. So
of
that is,
the data
Mm.
and all possible labeling of the data, that's the definition of a CRF, or a segmental CRF.
So, but yeah, I mean here I consider the scores anything, but maybe the CRF came from the maximum entropy models where the features
Right.
basically are zeros or ones, and
Yeah, I mean, you can give it
yeah.
either zeros or ones or real.
the phone looks like a segmental,
Mhm.
yeah.
And also it's important to note that here I don't normalize I don't compute the posterior for each segment, because if I did that, I'll get the score diminishing as I get longer sequences, because I'll be multiplying probabilities.
But then you do this normalization.
Yeah, because I saw some work, but it was frame based, that computes posteriors for each frame, and then multiplies the posteriors of the whole sequence. But
Right,
here
see,
I
you can't do that because that is bad.
yeah.
But
Here I leave the neural network to decide the range of the score. So if it sees, for example, some nice segment, it will give score higher than 0, which will actually will be preferable to include this segment in the sequence.
right. It's not necessarily the case that when you have one of these models, fewer labels gets higher score.
But this one will happen. For
Because
this
you do
model,
the
it doesn't happen.
normalization.
Did it happen to you for sure? That one having more score?
Typically, well, if you want to,
Like,
if you have
But that, right, that's
product of
why he had to
scores.
introduce
I think that's all.
these antiphones and do this other kind of stuff.
This
Essentially,
one
the normalization gets around the whole
Mhm.
anti-phone problem and the normalization problem.
So in both cases.
Yeah, it has
no problem.
much similarity with the CRF models, but here, like I think in it as neural network score, so that the neural network will try to infer what is the good score range compared to other labels. So here for each segment I have some segment score like this and some language model score. And in my experiments I use the simple language the simple bigram language model.
A lot of decisions that have to be made in terms of how to complete the math.
Yeah, here
The
the current problem that we have neural network scores for each frame. So maybe there are many ways to compute this S for the whole segment. So the first simple method is to get the middle frame. So for example, if I have this segment boundaries, I consider the score in the middle frame as the score for the whole segment, depending on the neural network that it sees a long window, for example 15 frames, so it can decide whether this segment is whether this label is suitable for this segment or not.
So just how would you complete that one in this case? I think you also have neural network.
We use them as detectors, so the thing like Phoenix Kreminsky and one of the students had some neural net phone detectors, and if it detected a phone,
Mhm.
we gave
Just
it
a
a
frame
one.
level, it's not a segment level. And that's what difference.
The neural network is like operated as blue.
What?
Yeah, the
So this is
neural network is
neural
operated as a
segment level. I think that's a bit different.
No, it was operating at the,
So it had one, it put one, otherwise it would be zero. As long as it occurs in one second.
so it was like one phone would go up in probability, and there would be the maximum probability, and then it would go down. It would be the maximum for some time. And we said, okay, we detected it at the center.
And then put the one,
Mhm.
you put the one,
And then
or zero.
it means, oh, there's detection of this phone at this time. And then if you have a segment that spans that,
Get the
then
maximum.
when you're computing the segment score, you might have a feature like the word contains phone X, and I've detected phone X in this span. Or
And
the
it's completely different.
And then you put a one or zero in terms of
well, I don't
number.
think it is. I
No,
think-
here this numerical value, whatever, we got that.
Right, I think it's,
And this, I don't like that.
there's a lot of ways that you
Yeah,
can,
yeah.
there's
Yeah.
a lot of ways that you can take a bunch of numbers in a segment
Yeah,
Yeah,
yeah, yeah.
and boil them into,
Yeah, right.
Do you have better way, one of the best ways to segment the CI? That might actually go to here. Here we have no idea what the best way of doing it.
yeah, no, I think, I don't know what the best way is. I think it's, I mean, you could imagine middle frame, you could imagine average, you could imagine median.
Yeah.
you
If
could-
I did all this.
This, by the way, is also a little bit like what these NTP visitors that Mike had did, but they didn't do it at the segment level, they did it at the frame level. And essentially, at the frame level, they had it at the state in each state in the finite state language model that they had, they learned a max-n function that combines a bunch of feature weights extracted from the plane. So it was similar in the sense that it was using a CRF type thing to combine a bunch of weights extracted at some level, but it was different in that it was go at the frame level, not at the segment level.
This is real segment level.
Right. From the NTT.
The
So you saw the NTT guy.
An entity is roughly this entity is doing an arc is doing
Yeah, but
the
that,
story that yeah, it's a
Is that a segment or right?
was fine.
Right. But here we are, he's trying to get rid of the frame altogether.
Sure. No.
You get the whole segment, whatever, I think
Right.
that's tough.
Yeah, but the disadvantage of this method that if the segment is longer than the neural network, so it may skip some other phonemes.
And also, I thought that one of the nice properties of segmental CRF that I really like, if this one cannot put in there, is that the feature is a function of both the input and also the output. So you might have labels depending on the feature. So if this label, you have it. This one, we don't know how to do that. Can you do that? So saying that, for example, there's some format on the other, not only just you said that, well, if there is, if this label.
In that case, you
is
can.
some kind of vowel, you also call it that feature. But if it's not that kind of,
In that case, you can connect
the solo sound. You don't
some neural network nodes to the certain phonemes, but I mean the neural network is assumed
and
to.
that can put into here. Fine. So I said some format information can put into here. But some other sound I don't even put in there because I think that's part of format.
Yeah, the assumption is that the neural network will learn
Yeah, you learn.
which features goes with which labels.
So do you use in segmental CRF to use this kind of label depending on feature? Absolutely. To show that's very important. So in certain features, in certain labels, you don't even define those features. Then you're just missing a particular term. So in general model, it's horrible. Total,
Right.
horrible things.
Right.
Don't know what it is. But here,
Right. No, in general, you can throw in lots of features and have some that are active in one condition and not active in some other condition.
depending
then
on the label.
hope-
Depending on the label.
Then the thing is, you got to hope that your regularization will then move the weights of nuisance parameters to zero. So that there's a little bit of there's a little bit of an art in,
We don't know how
in
to
the
do that.
regularization, but I would
Yeah.
say it's less of an art. Less of an art goes into regularization than it goes into some of the other stuff.
Okay, let's go through here.
Okay, so this is the middle frame, and I can assume that T is in this model. I can assume that Ti is the position of the score. So Ti minus 1 and Ti are not the real segment positions. They are just the times that I pick the score, the best score for that segment. So this model is actually more flexible, and actually it is more simple and fast for implementation. And other methods to get the segment sum. I just sum the scores along the whole segment, or the other model to get the average. I divide by the segment size.
So segment CRF, you can try all average or something.
We tried some, but not definitely.
Have you tried something like
Definitely not.
majority vote or something like that?
No.
So this is something I really want to try, but right now time for me to do it.
And also we can use duration model scores, but in my experiments I didn't use them. And also this model allows more complex models, but it will be slow and for rescoring only, to get segment-dependent neural network outputs to combine. Maybe to normalize the segment size as an input to the neural network. Then I compute one score for the whole segment, and then add some frames for right context and left context. But this is for future work. Learning of this model is simple. I just the derivative of relative to the segment score is just probability of all alignments that contains this segment with this boundary over the probability of this label minus the probability of this segment happening with any label sequence. And this can be for bigram language model. This is easy to compute using modification of forward and backward algorithm. So I'll compute alpha at the beginning of each segment, considering summing all the previous parties, and some alpha at the end of each segment, considering all the segment durations, like in this figure. So the summation of all possible passes up to time t, I can compute them by considering all durations and computing the segment score for this duration. And for each one of these, I compute alpha start of the segment, which considers all possible label histories at this time, which is just multiplication of all alpha end of the previous segment multiplied by the language model weight. So the learning will be just after computing alpha and beta, I can compute this term using this equation and this term using the alphas and beta and segment score. And also language model can be computed easily by summing all alphas, summing along the whole time sequence of the previous segment alpha of the previous label multiplied by the beta of which is the summation of the sequence. Yeah.
So that kind so this kind of learning simulation technology.
Yeah, I'm just sending you the reference.
Okay. Okay, that's good. Thanks. So now I have this derivative for the top nodes of the neural network. Then I backpropagate this derivative to train the weights. And then for decoding, it's similar to the forward algorithm, but replacing max, but using max instead of sum. So here I use max instead of summing all sequences. I find the max and keep track of it for both the previous label and for the segment duration.
Totally trivial, just like standard, gym class, that kind of the old model.
Yeah, it's only the additional dimension of going through the duration. Yeah, by the maximum duration. And I did some experiments on timid dataset. I used only state labels as segment labels. I didn't use any time alignments. And I didn't implement duration model yet. And then I got these results.
Yeah, not very good.
For the last frame, I got 25%. Against the baseline, which the baseline is the deep neural network, the hybrid HMM deep neural network. For the same number of layers, I get 23% error rate. And here I get 25.
So
This is without language model.
one trick
Mhm.
that's useful is if you have a baseline, to build the baseline in. And I think in this case you could do it by basically adding up the frame-wise scores, right? If you do an HMM decoding using neural net likelihood,
Mhm.
then the HMM acoustic score is the frame-wise sum of those log likelihoods.
Yes.
And so if for each segment you define a feature that is, the label is X, and the frame-wise sum of the scaled log likelihoods is line, you put that in as a feature.
Mhm. As a score.
That will give you the identical acoustic model score as your baseline.
You cannot lose.
And you cannot.
Yeah. So actually,
You should do it, yeah.
actually, the segment sum is same as the hybrid HMM neural network decoding. The decoding is the same. And when I
What's your baseline? Your baseline number.
that I'm comparing against
Right.
the hybrid, the baseline number is 23%.
Right. So you take the acoustic scores from that 23 system, and you use those, not those acoustic scores.
I did that, and I got the same result for segment sum. I mean, when I throw away the state transitions, which contains implicit duration model and the language model, I get similar result as the segment sum.
No, I'm sorry. I think Jeff has this is very, very wise. So go back a few slides to see SAO, please. So Jeff, you're saying.
Which one?
Back one more. Back one
Yeah,
more.
here.
Like somewhere here.
Right there.
Yeah, right here.
So there.
Mhm.
You say you
You say that I use the HMM scores here. Sorry, the neural network scores here of the previous baseline model
right.
directly.
Without doing the submission. But that will be
With the
You do need to do
you do need to do the
and that is the result.
And not-
segment
and-
of the segment.
and not with the, I don't know if there was window in there or not, but it's not the same window. So there's no reason for the
What do you mean? Like the same one is the 11th range or 15th range.
right, what I'm saying is there's no reason for the segment baseline ever to be worse than the
So
non-segment.
why not? I mean, because
Because the tuning is different. Why is
Okay,
tuning
so-
tuning
The okay, there are some differences.
Oh, you can't, I guess you can't do the back propagation.
yeah, exactly. If you don't know,
You have to
that would be
fix,
yeah.
you have to
Yeah,
fix
fix
those
that one.
scores.
So
I see.
so the
Otherwise, the way you're suggesting, according to your suggestion, there's a mismatch between training and testing, right? Because-
That's why if you use hybrid system you get 23, and you use segment sum you get 25.
Right, my point is that the hybrid system is itself a segment sum system, because it sums the scale of likelihoods of each segment.
yeah. It is one
And
One
so
type.
that means that this segment, this model is a superset of that.
yes.
And so if you initialize this model to that,
And then we
No,
don't do
very
anything.
different, no.
and you don't do any training,
And then
you
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 do-
should get the same.
No.
And-
It's very different because the decoding procedure is different. In that,
The decoding is the same
you
if I use the
have
segment sum.
which is considered in the hybrid system, which is not considered here.
No, you have to include the scale likelihood.
If it's secure likelihood, then it's different than what we are trying to do.
Well, whatever prior you use, you can stick that in there also.
But then it's a different meaning. You can get the same result.
No, just mechanically, would it be the same mechanically?
It should be identical.
Identical.
It
But
should
if
be,
you don't train anything, right?
right, it
If
should
you
be
don't train-
possible if you don't train anything.
No, but on the other, you just out, you sum up all the O, so the score becomes everything. So maybe,
No, for the segment
go,
sum.
Go back to the equation. So if so you're saying that you multiply that one, the first, maybe this one.
Yeah, the first one is very similar to the hybrid HMM neural network model.
No, but you get a summation over could be how many
Yeah, and HMM I do the same.
You have it over 6, so your O gets mirrored. So how can you be
No, here I don't average.
Same as the hybrid.
This is the average. Here I average, but here I don't average.
No,
the segment-
average you smear out, but the whole point is that you smear out, you don't get exactly what the score that just measured, individual OT. You don't have OT anymore.
Here I do the summation.
It's the same. If you don't divide by 5, it's the
I see. No, but if O change, from within segment to go from here to here, right? And then when you take average, it becomes flat. That's not good. Because maybe that information is useful to begin with. When you average.
What do you mean by average?
Uh,
Average is different.
Yeah.
It's
The
not
average is different.
Yeah, yeah.
Yeah,
Average is different from sum, and you don't want to do the average. If you do the average, you'll get weird things with segment lengths.
Here? You mean here? Actually, I got better score.
From the point
Yeah,
of view
yeah.
of making it match
Yeah.
what the baseline
Yeah,
is
yeah,
doing.
yeah.
The baseline's not doing any averaging.
Mhm,
It's
mhm.
over segments. The baseline is just adding things up.
Mhm.
I see. When you add up things, I
So,
see.
so my main point is that you can emulate the baseline.
Yeah,
by
actually,
adding things up.
I emulated the baseline by
I see.
getting the duration from. No, actually, not getting the duration. Using the transition probabilities for each state,
Right.
and use it as a duration score, and I got the same result as the HMM.
As a baseline.
Yeah,
In the end,
yeah,
23%.
yeah. No, the 23% for an
So
average.
what do you do again? What do you
So what is missing in this table? Here I didn't use the language model nor the duration model, but HMM has an implicit duration model and has a language model. So in the next and also HMM is initialized using alignments that it gets from HMM. I mean the hybrid DNN model. When I train the DNN, I get alignments. But here I didn't use any alignments. I just initialized from random.
Here you are doing the same thing. Yeah, this is something I suspect something is correct. Every time you talk about DNA to machine learning people, they always the first question they ask is how do you count? And they count not in most of DNA stuff you testing is coming from each other alignment, and that's not good. So it's nice to get results all together. And this framework, it actually started in a very brave. Okay? All segment is gone. Just use first frame and the end frame to do all this. That's crazy. I mean, as I mentioned, it's very useful. It's not always, but the mathematical formulation of that second model doesn't require that at all.
Mhm.
And that actually,
The definition of the cinematic also doesn't require that.
Yeah, it doesn't, but it helps.
It's
You can start.
no,
yeah.
you do. I mean, ideally you don't, but you have to initialize the mature model sensibly, not just taking a flat. But just for segmental CIF, do you need to do that? Yeah. When you do this recognition in terms of initialization, how do you stop training? I mean, you also have full model. Right? Full model is training. Do you make use of segmentation information from HMM to begin with in the training? You know?
So there were two different things. There's stuff that I've done at the workshop
Yeah.
and with Patrick.
Yeah.
And there we use lattices constrain search space over words.
Okay, so you
Then
don't have
there's-
segmentation there.
Right.
That has
Then there's
segmentation
follow-on work that I did myself,
there. Okay.
where
Sure.
at the phone level, where I just did all possible segmentation.
But did you see what it says?
That's a decoding. How about the training?
For training.
That's why the number is really wrong. That's why I suspect what happened. Because this is extremely, I know, HMM actually does that as well, but you have to initialize HMM first. Otherwise, if you use maybe zero, initialization for everything, HMM is not reasonable. Typically, the best HMM is that people do from the second.
It will work, but
Actually can. Like,
but not so good.
Yeah, I tried before. I mean, normally people do uniform segmentation. From that, you can start doing it. I don't know. Maybe it is. So I don't know whether that may be due. So actually, he tried something, he did some strength.
But I found today that there was something wrong.
You
Yeah,
must have bug there.
yeah.
So this
I
is
had
tricky
something,
part
yeah.
of information.
Yeah. So yeah, and
Okay. So
I'll try maybe today or tomorrow
okay, so
to
this number has to
solve
go
this.
up. Yeah, it has to go up. Okay.
But I discovered that the duration model is important to get good results.
Okay, and then what kind of weight do you put in the duration model?
No, I mean compared to HMM, because when I used state transitions, which represents an implicit duration model, I found, I mean, when I throw this information away, I drop 1.5%,
Oh, I see.
which is the difference between this model and
I see. Oh,
the HMM.
okay.
So here I try to use the
bigram language model. Here I just use the log probability of the bigram language model that I get from HTK, and I get 0.74% gain.
So you mean some, so what is so low? Oh, 2 hidden layers. Okay.
Yeah.
Oh, so the DN, okay, I saw.
Yeah, this is the DNN with
The
2
DN,
hidden layers.
okay,
Yeah.
Okay, okay. Okay, so the last number in at least.
This is for convolutional neural network.
Yeah, nothing to beat that.
Yeah, I tried also to to learn the language model metrics from this derivative. Here when I do the same, I mean at the same time of training the weights, I lose some score. I got worse results. I think because in the early epochs I go to also updating the language model after each utterance is not good because I have limited language model information. Here I did update language model for using the whole epoch after the whole epoch, but I do interleaving epochs for weights updates and language model updates. I get this score, which is very neat.
In the segmental CRF work that we did gradient. We used rplot basically in this batch mode, so we computed the derivatives over everything and do an update. And we're using rplot to control the.
What's our problem?
It's a fast doing gradient descent.
Oh, yeah.
It basically maintains a step size for each parameter.
Yeah.
And if you go in the same direction
Yeah.
twice, you multiply that step size by like 1.1. So having adapted step
Yeah.
size. And that was always very stable. And I'm wondering, I guess Don, you brought this up.
For the language model too?
That for language model and for all the parameters. That now the training is being done with a different objective function than it started with. And in particular, the training of the acoustic model parameters in the neural net. In this segmental thing, because back propagating is going to adjust those likelihoods, the scaled likelihoods that go in. Have you tried not adjusting those, just like freeze them and treat them as features and just learn?
Yeah. This is the first score. I just get the HTK language model log probabilities, the bigram language model, and I freeze it, and I got this.
Is this back propagating into the neural net that's looking at the actual acoustics?
So I use this score to compute the delta, the back propagated derivative, and I back propagate only for the neural network weights, not for the language model.
Right. What I'm wondering is maybe it would even be good to just freeze that neural net and just learn weights on.
Yeah, I tried that. It didn't go much. It overfits. Just when I try to do that, it immediately overfits.
But wouldn't that be less overfitting because you're not back propagating, or you're just
because the neural network reached the top of when I try to optimize it any parameter. When I try to optimize it anymore, I just get better result on the training data and worse result on the development side. I mean, here I try to do that. I have a trained neural network model without any language model, and then I try to update the language model alone. I got very small improvement.
But what about
0.05?
the neural net that's computing phone computers? Never
Random neural network, you
No,
mean?
you have your trained neural net,
Mm.
and you compute the sum score of what it's outputting, and maybe the max score of what it's outputting, stuff like that.
Yeah, here I didn't update the neural network.
And but you don't update the neural network. You don't do any back propagation.
Yeah. Here I did
That was
that. Yeah.
Let's go back.
Maybe because, I mean, here the language model is bigram, and maybe the neural
So
network.
it's still not work.
Well, let me go back a few slides. Just want to make sure that I understand what works here. So go back almost like about four backward. Go back. So okay. So no. Next slide. Yeah. Next slide. So this one. So
Yeah.
So Jeff, you are saying that you omit a few steps here. Is that what I mean?
What I'm saying is, he said when you learn the language model with something like that, you don't update DNN. You assume the DNN score is fixed.
Right, just freeze the CNN.
Okay.
Yeah, I did that. And
Freeze the CNN.
yeah.
And then learn
The other way.
the other way, or learn.
Yeah, the problem is that this matrix is 61 by 61, so I think it has enough number of parameters to overfit a well-trained model.
But if you freeze the DNN.
Yeah,
But
yeah,
you
even.
still learn the weight of the DNN score. That
Right.
weight is 61 by
Oh, and
61.
you're saying that's still enough to overfit.
Yeah, yeah.
I see.
So I didn't see your. Did you write down the formula for the derivative with respect to neural network weight? Do you have anything?
Yeah, so
You have a slide there. Somehow it makes this one go back.
sorry.
The learning of the neural network weight. How it
Yeah.
differs from the regular way of doing it.
It only differs of
Oh,
the
output, and then
derivative
everything
of
else is
the
okay,
top
so-
layer.
Okay, everything else.
Then everything else is
Okay,
the same.
And treat that
Mhm.
as if you just modify the target.
Yeah.
Okay.
So
Coding probably similar to.
So that's it. Just a summary, the proposed new segment-based speech recognition model. Maybe it is not completely new. It's very similar to the CRF. But here the model is more suitable for the neural network, so that the advantage, it is probabilistic segment model. I don't have any invalid, I mean, I don't put any invalid assumptions other than the power of the, maybe the language model and the duration model scores. And no need to convert the neural network scores back to likelihoods. It solves scores dependency issues. I don't have these issues here. For example, here I can freely use language model that not only depends on the previous labels, but also depends on the next labels. And I think the hybrid model is gets better score because first it learns from, I mean the score for hybrid model, I start from forced alignments, so the neural network have more clear targets in the beginning. It has implicit duration model in the transition matrix, and I didn't use a duration model yet. And methods to improve better language model, maybe using duration model, and finally the future work of to compute a segment-aware neural network score, as I suggested before. Okay, that's it. Thank you.